Good day, sir. I am Haider Sega from BSE YouTube, and I will now discuss my answer on pressure. So, problem number 28. As illustrated, a mercury manometer is attached to the side of a nearly full water tank. The reading of the mercury column is 15.5 inch of mercury gauge. Although air on the water maintains the pressure, on the other 10-inch leg of the manometer is full of water. For the water or the H2O, the density is equal to 62.3 pound per cubic feet, and for the mercury, the density is equal to 846 pound per cubic feet. If the location is at standard gravity and the temperature of both the water and the mercury is 60° Fahrenheit, what is the pressure in the tank at the level where the manometer is attached? If the tank extends 10 feet below this level, what is the pressure at this depth? So for the pressure where the manometer is attached, the formula is the density of the water times the height plus the density of the mercury times its height plus the atmospheric pressure. And since the height are in inches, so we have to convert it into feet. And well, for the height of the water, since there is 10 feet here, so we have to convert it first into inches. So 10 feet is equal 1 feet is equal to 12 inches. So 10 times 12 is 120 divided by the is equal to 120 inch divided by the 10 inch here. Then the height of the water is equal to 110 inch. So we have to convert it back into feet. So it will be divided by 12. So from the given, from the problem, substituting all the given. So we have now the P is equal to 1,663.83 pound per square feet. So in order to add this value into the atmospheric pressure, which is equal to 14.7 pound per square inch, we have to multiply it by 1 feet squared divided by 144 inch squared. So this will be cancelled, and the unit now will be pound per square inch. So the P1 therefore, or the pressure of the tank at the level where the manometer is attached, is 26.2544 pound per square inch. Now for the pressure at the bottom, the formula is equal to the density of the mercury times the height plus the density of the water times the height plus the atmospheric pressure. So from the problem, substituting all the given, so we have the density of the mercury, which is equal to 846 pound per cubic feet. Its height here is 15.5 inch, so we have to divide it by 12 in order to convert it into feet, minus the density of the water, which is equal to 62.3 pound per cubic feet, and multiplied by the height of the water, which is equal to 10 inches, and divided by 12 in order to convert into feet, plus the atmospheric pressure. So the P at the bottom now is equal to 1040.8333 pound per feet squared. So from the previous equation, again we have to multiply this in order to add into the atmospheric pressure by 1 feet squared divided by 144 inch squared. So this will be now cancelled, and the remaining unit will be pound per square inch. So the pressure at the bottom now therefore is equal to 21.928 pound per square inch. Now next is a 30-meter vertical column of fluid with density of 1,878 kg per cubic meter is located where gravity is equal to 9.65 meter per second squared. Find the pressure at the base of the column. In order to find for the pressure at the base of the column, so the formula is equal to P, or the pressure at the base, is equal to the density times height times the gravity, or the gravitational acceleration. So substituting all the given from the problem, we now have, so the pressure at the bottom or pressure at the base therefore is equal to 543.7 kilopascals. Next, a weatherman carried an aneroid barometer from the ground floor to his office atop the Sears Tower in Chicago. On the ground level, the barometer read 30.150 inch of mercury. Topside, it read 28.607 inch mercury, or the absolute mercury. Assume that the average atmospheric air density was 0.075 pound per cubic feet and estimate the height of the building. So in order to solve for the height of the building, I have to first determine the delta P, or the change in pressure. So that is from the first reading, which is equal to 30.150, so minus the 28.607, so which is now equal to 1.543 inch mercury. So we have to convert this into pound cubic feet. So 1 inch of mercury is equal to 70.7262 pound per cubic feet. So we just have to multiply it. And now we have 109.1305 pound per cubic feet. Now, in order to find for the height, so we have the formula pressure is equal to density times height. So transforming in this formula in order to find for height, so height is equal now to the change in pressure divided by the density. So since we already have calculated the delta P, just have to substitute it to the formula. So the height therefore is equal to 1,455.0736 feet. Next is a vertical composite fluid column whose upper end is open to the atmosphere, is composed of 18 inch of mercury with a specific gravity of 13.45, 26 inch of water with a density of 62 pound per cubic feet, and 32 inch of oil with a specific gravity of 0.825. Determine the pressure A at the base of the column, B at the oil-water interface, and C at the water-mercury interface. The specific gravities are relative to 62.4 pound per cubic feet of water. Since the order of the liquid are not mentioned, so the order would be, the densest would be at the bottom. So the order would be the mercury at the bottom, followed by the water, and oil at the top. So in order to solve for the pressure at the base, so it is equal to the density of the mercury multiplied by the height plus the specific gravity of the water times the height plus the density of the oil times the height plus the atmospheric pressure. So substitute all the so from the problem we just have to substitute all the given. So we now have here total of 1,530.9667 pound per square feet. So in order to add this into the atmospheric pressure, we just have to multiply it again by 1 feet square divided by 142 square inch. So the pressure at the base therefore is equal to 25.3317 pound per square inch. Now for the oil-water interface. So when we say interface, it is the region between the two liquids. So the oil-water interface is located here, and this blue line. And in order to solve for this, we just have to find the pressure of the oil. So the oil-water interface now is equal to the 32 divided by 12, since the height of the oil is in inches, we have to convert it into feet, times the density of the oil times the density of the water plus the atmospheric pressure. So again, in order to add this into this one, you just have to convert this pound feet into inches by multiplying 144 square inch. So the oil-water interface, the pressure of the oil-water interface now is equal to 15.6533 pound per square inch. And for the water-mercury interface again, so the water-mercury interface, so this is the region, or this is the water-mercury interface. So in order to find for the pressure here, so we just have to add the pressure of the water and the oil. So the pressure at the water-mercury interface is equal to the height of the water divided by 12 to convert it into feet times the specific density of the water plus the height of the oil divided by 12 to convert it into feet times the density of the oil times the density of the water plus the atmospheric pressure. So again, in order to add this one into the atmospheric pressure, we have to convert this feet into inches by multiplying 1 feet square divided by 144 square inch. So the water-mercury interface, the pressure at the water-mercury interface now therefore is equal to 16.5862 pound per square inch. Next, a simple mercury manometer connected into a flow line gives readings as shown in the figure. Local gravity, standard, and the mercury density is 0.488 pound per cubic inch. Find the pressure at points X and Y when the flow line and left leg contain A, air whose density is 0.072 pound per cubic feet, and B, water whose density is 62.1 pound per cubic feet, and C, answer A and B if the local gravity ID is equal to 30 feet per second squared. Now for A, we just have to, for the PY, we just have to add the atmospheric pressure by the density of the mercury times the height. So, substituting all the given, the atmospheric pressure, which is equal to 14.7 pound per square inch, plus the density of the mercury, which is equal to 0.488 pound per cubic inch, and the height of the mercury, which is equal to 25 inch. So Py now is equal to 26.9 pound per square inch. Now for the Px, for the pressure at the x, is equal to Py plus the density of the water times the height. Now the Py, as we already solved previously, is equal to 26.9 pound per square inch, minus, since it is upward, so 40 minus 25 is equal to 15 inch. Now, performing the operation, the Px now is equal to 26.9 pound per square inch. Now for the B, here, for the water, you just have to, the Py is equal to the atmospheric pressure plus the density of the water times the height, plus the density of the mercury times its height. So from the formula, from the problem, substituting all the given. So since it is stated here that we must use the 62.1 density of water, so here divided by cubic inch in order to convert this feet into inches and to add into the equation. And then so the density of the height of the water, again, as I previously discussed, is the 40 minus 25, which is equal to 15 inch, plus the density of the mercury, which is equal to 0.488 pound per cubic inch, times the height of the mercury, which is equal to 25 inches. So performing all the formula, so the Py now is equal to 27.439 pound per square inch. Now for the Px, it is equal to Py plus the density of the water times its height. Now for the Py, we already, as we previously solved, have 27 pound per square inch minus the density of the water, which is equal to 62.1 pound per cubic feet, and divided by cubic inch 12 cube in order to convert into inches, multiplied by the height of the water, which is equal to 40 inch. So performing all the operation, the P of x now, the pressure at x here is equal to 25.56 pound per square inch. Now for the letter C, so the formula for the gauge pressure is equal to the density of the mercury times the local gravity divided by the gravitational constant times the height. Now from the problem, or from the given, the density of the mercury is equal to 0.488 pound per cubic inches, multiplied by the local gravity, which is from the given, is 30 feet per second squared, multiplied by the divided by the gravitational constant, which is equal to 32.2, and multiplied by the height of the mercury, which is equal to 25 inch. So the P gauge now is equal to 11.36 pound per square inch. Now, in order to solve for the absolute pressure, so it is equal to the atmospheric pressure plus the P gauge. We already have the P gauge here, and the atmospheric pressure is 14.7 pound per square inch. So now the absolute pressure is equal to 26.06 pound per square inch. Next, a manometer containing water with density of 62.1 pound per cubic feet and mercury with a specific gravity of 13.55 connects to pressure regions A and B as shown in the figure. The local gravity acceleration is 32 pound-feet per second squared. If PB is equal to 50 pound per square inch, find pressure at A. So this is the figure for this problem. So for the pressure at A, have the formula PA plus the density of the water here times the height minus the specific gravity of the mercury minus, since it is upward, times the density of the mercury times its height plus the density of the water, since it is now downward, times the height is equal to the pressure at B. Now substituting all the given to the formula. Now since the given height is in inches, so we have to divide it by 12 in order to convert into feet. And transferring the P of transferring the P of A to the other side of the equation. So PA is equal now to negative 62.2 pound per cubic inch. Now transferring P of A to the other side of the equation, and performing all these operations, we have 1014.3 pound per square feet. Now, in order to add this into the pressure at B, which is already given, which is equal to 50 pound per square inch, we have to convert this into inches by multiplying 1 feet divided by 144 squared inch. So the pressure at A now therefore is equal to 57.04 pound per square inch. Next, the same as 36, except that value of the mercury. The fluid is a special compound with a specific gravity of 2. From the previous problem, pressure at A is equal to the negative density of the water times the height plus the specific gravity of the mercury times its density times its height minus the density of the water times its height plus the pressure at B. Now substituting all the given to the formula, so except for the density or the specific gravity of the mercury, which is equal to 2. Now The pressure at A is now therefore equal to 48.74 pound per square inch.